Among the many different domains that people apply LLM-based AI to, I think healthcare is one of the most promising, especially when it comes to AI as a personal health assistant. The main reason is that this is a space where humans and AI naturally complement each other without getting in each other's way. AI is good at processing and keeping track of huge amounts of technical information instantly. It can help connect someone's personal health conditions with the latest scientific knowledge and do it at scale, something that would be impossible for human doctors only. But to get there, we have many obstacles to overcome. In the past videos, I discussed two AI doctor systems. Both had slightly different focuses, but neither of them dove very deep into the many different ways such systems can fail. The goal of this video is to get a holistic view of the current understanding of failure modes in these systems by going through recent research papers on clinical reasoning AI and to see how we might fix them. I've gone through most of the literature in 2025 and compiled a list of papers that I think best represent what we know so far. Now, over the past few years, studies proposing new systems of health AI have been popping up rapidly, and the systems themselves are getting more and more complex. A health AI is far more than a single large language model. It's everything around it: the external data pipelines, multi-agent flows, and many more. And 2025 is the year when we finally started to see more papers challenging or warning about these systems from different angles and perspectives. Let's take a look at the first group of papers that I have here. We have three recent studies evaluating the broad clinical reasoning capabilities of large language models. These studies come from some reputable institutions and were conducted by domain experts using real-world data and rigorous methods. And they all come to roughly the same alarming conclusion: LLMs may not yet be ready for real-world healthcare applications. The first paper evaluated LLMs using a test format called script concordance testing, SCT. It is a format used to measure the clinical reasoning abilities of students or professionals in the domain of medicine and healthcare. Unlike standard medical benchmark questions, these SCT questions emphasize decision-making under uncertainty. The test taker, in this case the LLM, must determine how new information changes the likelihood of a certain initial hypothesis. Also, the dataset or the questions used in this paper are international. The SCT benchmark used spans North America, Asia, and Australia, covering a range of generalist and specialist contexts. The geographic and clinical breadth enhances the benchmark's ecological validity, especially as reasoning patterns and clinical heuristics often vary by settings, by different languages or regions. But this format is not without flaws. For example, the SCT format itself introduces potential scoring artifacts. Expert panels tend to avoid extreme responses. Basically, the correct answers of these tests encourages conservatism and may potentially inflating scores for models that mirror this kind of conservatism. In other words, models that tend not to generate extreme responses. But overall, the result does provide a new angle to test the model's abilities and compare with humans directly. The second paper from Harvard and MIT presents the first large-scale systematic study of chain-of-thought reasoning for clinical text understanding. They assessed 95 advanced LLMs on 87 real-world clinical text tasks, covering 9 different languages and 8 different task types. As you can infer from the title, results from evaluations using the real-world data were not in favor of the AI. The main finding was that LLMs, when reasoning or thinking explicitly for too long, tend to make more mistakes. Mistakes include those related to clinical abbreviations and numerical reasoning, as well as general hallucination and information omission. The third paper from Stanford takes yet another different angle. Instead of building new datasets and novel methodologies of testing, the team focused on stress testing the reasoning capabilities of LLMs using existing multiple choice evaluations. They asked the question, do these models actually reason through medical problems, or they are simply exploiting statistical patterns in their training data? And the results show that when the models are forced to reason beyond familiar answer patterns, all of the models demonstrated declines in accuracy. So, with such high quality evaluations from these big labs, does this mean LLM-based medical AI systems are doomed? Well, it's nuanced. First, notice that all these studies focus on the LLM itself, not on the complete medical AI systems. That means they're evaluating the model in isolation, whereas any serious real-world medical AI product today will include much more scaffolding components around that. Next, consider the models tested. The first paper does use some strong models like Gemini 2.5 Pro and O3, but not all latest models, including GPT-5. The second and third straight up didn't test any of the latest models, including Gemini 2.5 Pro and GPT-5. That is not to say that these results are not valuable though. They are validations of knowledge and intuitions previously acquired from general AI systems. The insights or issues pointed out about these models probably still exist in latest models to some extent as well. For example, one recurring topic across these research works is the chain of thought COT reasoning, a technique for models to think before answering. The fact that this technique can be a double-edged sword in general has already been observed way before, and the above experiments helped confirm that with domain-specific real-world data. With a little help from insights from research on AI's capabilities in general, we can infer that the future likely involves training with tighter alignment and monitoring of an AI's reasoning process, maybe even somehow visualizing it, lowering the risks while keeping the accuracy gains. Beyond research into broad clinical reasoning capabilities, some other papers target more specific aspects. For example, one study focuses on how well AI understands medical-related temporal information, assessing the AI's ability for longitudinal reasoning. Another paper looks exclusively at models' ability to identify uncertainty and abstain, to understand when not to generate an answer. The above papers represent some of the most outstanding evaluations of clinical AI in 2025. But to build a more holistic view of all the failure modes, we would appreciate something that's more broad and more organized. And that's where survey papers can be helpful. These are works that already put together important failure modes of medical AI and solutions into clearly defined taxonomies or categories. Let's take a look at how different research teams tackle this task, which can be a very difficult and ambiguous one. The first survey paper is a very thorough compilation of everything related to medical AI, as you can tell from its table of contents. Their main focus is on hallucination, which is itself a fuzzy concept because there's still no universal definition, as the authors pointed out. Despite that, they were able to linearize failure patterns into this long list. From here, they identified the main sources of errors, data-related factors, model-related factors, and healthcare-specific challenges, such as medical jargons and abbreviations. Finally, each error source was mapped to mitigation strategies, which include improving data quality and curation, model-centric approaches including better training algorithms, prompt engineering strategies, external knowledge integration techniques, also uncertainty quantifications. The team also ran experiments on models that were relatively new, but still a bit outdated, and included basic search capabilities to better reflect real-world systems. Their key findings were like this. Advanced reasoning models maintain hallucination resistance leadership, meaning that the strongest general models still dominate. Also, chain of thought remains a consistently effective strategy. All of these are results that should be somewhat expected. Sadly, they also highlighted that domain-specific training still shows limitations compared to advanced general capabilities. While it is indeed expected for general models to still be in the leading positions over specialized models, I personally was hoping to see the specialized ones catching up. Thankfully, that is exactly what we'll find from the next paper. The second survey paper. This is a work that is more focused on the keyword reasoning. It breaks down the levels of reasoning required in medical settings in a clean, understandable, and first-principled way. It then maps a huge list of datasets and AI methods to those reasoning levels. As you may have noticed, every paper we've gone through evaluates AI a little bit different. The specific tasks and the setup vary, and this work beautifully summarizes all those evaluation patterns. I would recommend reading it if you want a very well-structured breakdown of most of the major aspects of a reasoning medical AI system. A nice breakdown of specific reasoning capabilities needed, of types of evaluation tasks, and of models and AI techniques, all in one place. Although this study also didn't test the newest models like GPT-5 or Gemini, a nice addition is that it did include domain-specialized fine-tuned models. The team found that these specialized models can actually outperform general models, especially on diagnosis-heavy queries. I'm excited about this finding and look forward to see how these specialized small models will evolve in the future, as I think they are key components to the future of AI in general. Check out a previous video more on this topic. Now, the final paper. This is finally a paper paying attention to the surrounding components of a practical AI system, specifically the multi-agent framework, which is something that can make the evaluation process far more complex. And the main findings are as following. Our investigation introduces a structured taxonomy of collaborative failures and a quantitative auditing framework that reviews a significant disconnect between performance and reliability. And they demonstrated that high accuracy often masks a fragile and flawed reasoning process, meaning that even though the model can generate accurate answers, that doesn't mean the reasoning process makes sense. That wraps up the papers I've collected, hopefully covering most of the major works in health/clinical AI in 2025. We're starting to see serious evaluations in the health medical domain that aim for real-world relevance, trying to catch up with the rapid pace of the development of general AI capabilities. But they still lag behind. Each has its own limitations. So what can we do? First, clarifying the goals and the positioning of such system is very important. The general direction should be that AI being a personal health assistant that can bridge the gap between the general public and advanced health knowledge, not as a replacement for human doctors. This lowers the bar for such systems to be adopted. They can already successfully serve the role of expanding and democratizing knowledge, and that doesn't require 100% accuracy. Then comes user education. The users should actively learn how to use these tools effectively. Just like we learn to communicate with people, we also need to learn how to communicate with AIs. The problems reviewed in these papers will be reduced in the future, but not completely eliminated anytime soon. As a user of these tools, you need to have a trust but verify mindset. More specifically, given a health AI system, you would want to look for structures and transparencies. What does that mean? Looking at the findings and methods from across all these papers, I like to put the solutions and mitigations proposed from these studies into these 4 layers: model parameters, test and compute techniques, scaffolding components, and UI UX. Techniques implemented at each level should be somehow communicated via the user interface, where well-educated users can use that UI for judging credibilities of the system. Check out my previous video for more discussions on structures of a medical AI system. Note that this user education direction is countering the direction adopted by a lot of big AI players with the goal to lower user burden. But given the probabilistic and statistical nature of AI, reducing user involvement too much may not be the best path. What do you think? Share your thoughts in the comments below.